Hello students, I am Dr. Geetu Gambhir and today I bring you the next learning episode in BSc Forensic Science on an important unit of the paper Technological Methods in Forensic Science, that is UV visible spectroscopy. This particular unit will be dealt in two parts. Dear students, in today's lecture, that is UV visible spectroscopy, in part 1, you will be introduced to UV visible spectroscopy and role of chromophores and auxochromes in the absorption phenomena. In addition to it, you will also be told about the absorption laws in UV visible spectroscopy, its instrumentation and techniques. We will wind up this module with a conclusion. So, students, let us have a look at the modules which we will be learning today. In the module 1, Introduction to UV visible spectroscopy, module 2, Role of chromophores and auxochromes in absorption phenomena, module 3, Absorption laws in UV visible spectroscopy, and module 4 with instrumentation and techniques, followed by conclusion in module 5. The spectroscopy is a branch of science that involves the study of interaction of electromagnetic radiations with matter. Depending upon the nature of interaction between the electromagnetic radiations and the matter, several possible processes can take place. These processes you have already studied in the lecture 6, such as absorption, emission, impedance spectroscopy, to name the few. We will now confine ourselves to the study of UV visible spectroscopy, which follows the absorption phenomena. Absorption takes place when energy from the radiative source is absorbed by the material. Extent of absorption is measured by measuring the fraction of energy transmitted through the material. Absorption will decrease the transmitted portion. This is known as absorption spectroscopy. For example, UV visible spectroscopy. Common UV visible spectrophotometers record the spectra over the range of 200 to 800 nanometers, that is UV region of 200 to 400 nanometers and in visible region of 400 to 800 nanometers. The recording of spectra for wavelength shorter than 200 nanometers is not practicable unless special vacuum techniques are used, as atmospheric oxygen strongly absorbs the radiations less than 200 nanometers. The UV visible spectrum is almost always recorded on a wavelength scale in nanometers. Origin of UV visible spectra. Let us try to understand how the UV visible spectra arise. It arises due to absorption of electromagnetic radiations in the UV visible region of the electromagnetic spectrum. The absorption of electromagnetic radiations in the UV visible region results in the transition between the electronic energy levels. In these electronic energy level transitions, the electron from the ground state of the molecule gets excited to the higher electronic state in the molecule. The most probable or common electronic transition is from the highest occupied molecular orbital, that is HOMO, to the lowest unoccupied molecular orbital, called as LUMO, in a molecule. A UV visible spectrometer records the degree of absorption by a sample as a function of wavelength lambda of light absorbed, and the resulting plot between absorbance versus wavelength lambda is known as UV visible spectrum. A typical UV visible spectrum is shown here in the figure 2. The significant features of UV visible absorption spectra are lambda max, at which the maximum absorption occurs, that is, the intensity of absorption is maximum. This absorption at this wavelength is represented by epsilon max, which represents the maximum molar absorptivity. These parameters are characteristic of a particular molecule. Wavelength at which the absorption occurs depends upon the energy difference between the ground electronic state, that is the HOMO, highest occupied molecular orbital, and excited electronic state, that is LUMO, lowest unoccupied molecular orbital. Larger the energy difference between the ground and the excited electronic state, lesser will be the value of the absorption maxima, that is lambda max. UV visible spectra generally consists of a broad band of absorption rather than the single sharp line for each such transition. The band-like structures of UV visible spectra arise due to the transitions taking place over the wide range of wavelengths rather than a single wavelength. This can be explained on the basis that each electronic energy level is in a molecule consists of closely separated vibrational and rotational energy levels. As a result, a molecule can undergo electronic transitions involving vibrational as well as rotational excitations at the same time. This results in a number of transitions that differ from each other only in very small amount of energy, giving number of closely separated lines that spectrophotometer can't resolve, and rather it gives a band like structure enveloped over these closely separated lines. Chromophore is a part of molecule or group of atoms which is responsible for absorption of radiation. The nature of chromophore is significant as it decides the wavelength absorbed. The absorption of electromagnetic radiation results in excitation of electrons from ground state to the excited state. This is dependent on how strongly these electrons are bound to the nuclei and in turn depend upon the nature of group in the molecule which is absorbing these radiations. The presence of some groups with chromophores as substituents may change the absorption characteristics of chromophores. Such substituent groups are called as auxochromes and they increase the intensity of absorption and possibly change the wavelength of absorption. We can thus say chromophores are responsible for absorption of radiations and auxochromes enhance the absorption. When electromagnetic radiations fall on the sample under study, some part of radiation is absorbed by the material, whereas remaining part is scattered or transmitted. UV visible spectroscopy involves the absorption of light in UV visible region of electromagnetic spectrum, which results in electronic transitions between the ground and the excited state of the molecule. This absorption of electromagnetic radiation is governed by some laws called absorption laws, which are described below. Figure 1 represents the process of absorption, transmission and radiation. Beer-Lambert's law, general absorption law for UV visible spectroscopy, is the combination of Beer's law and Lambert law, known as Beer-Lambert's law. This law states that the absorption of light at a particular wavelength by an absorbing substance is directly proportional to the concentration of the sample represented by C and path length of the light in the sample represented by L. Mathematically, log of I naught by I is directly proportional to product of L and C, or log of I naught by I is equal to a constant E L C, where E is the proportionality constant and is known as molar absorptivity or molar extinction coefficient or simply extinction coefficient. I naught is the intensity of incident light and I is the intensity of the transmitted light. Beer-Lambert's law can also be written as A is equal to epsilon L C, where A is equal to log of I naught by I and is also known as optical density or simply absorbance. Significance of molar absorptivity epsilon. Molar absorptivity is a constant which relates the absorbance A with the molar concentration C and path length of the light L in a sample. It may be expressed as A upon L into C. It is the measure of intensity of absorption, that is, larger the value of epsilon, more is the intensity of absorption. The value of molar absorptivity ranges from 0 to 10 to the power of 6. Transitions with molar absorptivity greater than 10 to the power of 4 are called high intensity absorptions, while transitions with molar absorptivity less than 10 to the power of 4 are low intensity absorptions. Units of molar absorptivity epsilon. Since absorbance A is dimensionless quantity, so molar absorptivity has the units of liters per mole per centimeter. Percent transmission of light. Since I upon I0 is the ratio of intensity of transmitted light and intensity of incident light from the sample under observation, thus transmittance of light by sample can be written as T as a ratio of I upon I naught. The percentage transmittance can be represented as percentage transmittance is equal to I upon I naught into 100. All UV visible spectrophotometers consist of the following parts. First, the source of radiations. The commonly used source of radiations for UV region is hydrogen or deuterium discharge lamp. For visible region, tungsten filament lamp is used. Monochromator. Monochromator separates the radiations from source, which consist of all wavelengths, into the individual wavelength. This single wavelength is then split into two beams. One beam passes through the reference cell and the other through the sample cell. This kind of instrument, in which the light emitted by the source is split up into two beams, that is the sample beam and the reference beam, is called double beam instrument. Detector. The main function of the detector is to continuously measure the intensity ratio of the beams transmitted through the sample cell and the reference cell. The detector is generally a photomultiplier tube, although in some instruments photodiodes are also used. Recorder. Recorder automatically records the absorption of light at each wavelength as a graph of absorbance versus wavelength. Figure 2 represents the instrumentation for a UV visible spectroscopy. For analysis procedure, sampling of substances is required. With this in mind, we will now be studying about the preparation of the samples for recording a UV visible spectra. In this section only, you will also be acquainted with the various types of spectrophotometers. Preparation of sample for recording UV visible spectra. For recording a UV visible spectrum, the compound, whether solid or liquid, is dissolved in some suitable solvent, which itself does not absorb the radiations in this region of wavelength under study. The choice of solvent depends upon the solubility of a given compound in that solvent, nature of the compound, and also on the region of wavelength under study. The most commonly used solvents are methanol, 95% ethanol, hexane and water. The solution of the compound is placed in a container or cell which does not absorb the electromagnetic radiations in the region under study. The sample compartment hence provides a light tight environment which restricts the addition of the stray radiations. Quartz cell of 1 cm path length is generally used for this purpose. The cells with the other path lengths are also available. Cells with the larger path lengths are useful for the analysis of very dilute solutions. Glass cells cannot be used as they strongly absorb the UV radiations. For reference, some solvents is taken separately in another quartz cell which serves as a reference cell. Figure 3 shows various types of the sample cells for the UV visible spectroscopy. Spectrophotometers. The spectrophotometer operates by comparing the amount of light in the beam transmitted through the sample with the reference beam which passes through the reference cell. This gives the amount of light absorbed by a compound at a given wavelength in the UV visible region. The typical UV visible spectrometer consists of a light source, a monochromator and a detector. The spectrometer usually employs a hydrogen discharge lamp as a source of light in the ultraviolet region of 200 to 400 nanometer, while tungsten filament lamp is used for the visible region from 400 to 800 nanometers of the electromagnetic radiations. As we have studied that the spectrometer operates by comparing the amount of light in the beam transmitted through the sample with the reference beam which passes through the reference cell. In this way, spectrometer measures the amount of light absorbed by the compound at each wavelength. This absorption gets recorded on the chart paper as a plot of wavelength of the entire region versus absorbance. The various kinds of spectrophotometers are described below. Filter photometer. Filter photometer is the simplest instrument for molecular UV visible absorption spectroscopy. This instrument has been named as it uses filter to isolate a radiation of a particular wavelength under which the study is required. The filter is positioned between the source and the sample. When beam of electromagnetic radiation falls, it allows the passage of a single wavelength through it. A filter photometer is often called as a single beam instrument as it has single optical path between the source and the detector. This type of instrument consists of only one sample holder for both blank and sample. The instrument needs to be calibrated before use. It is calibrated to two extreme values, that is to 0% transmission by using a shutter to block the source radiation from the detector. It is also calibrated to 100% transmission using an appropriate blank after opening the shutter. This sample is then kept in place of the blank and its transmittance is measured. The advantages of photometers are that they are relatively inexpensive, rugged and easy to maintain. Another advantage is its portability. There are some disadvantages of photometer as well. They include the inability to record an absorption spectrum and sources relatively large effective bandwidth, which limits the calibration curve's linearity. For recording a complete spectrum at all wavelength, mechanical system is required to rotate the filter which provides a scan of all desired wavelengths. Thus, this type of instrument works slowly and requires a lot of time to record a complete spectrum. Figure 4 represents the schematic representation of a filter photometer, single beam spectrophotometer. A single beam spectrophotometer uses a monochromator for selection of different wavelengths. The simplest spectrophotometer is a single beam instrument equipped with fixed wavelength monochromator. The calibration and use of single beam spectrophotometer is same as that of a filter photometer. The only difference is that it uses a monochromator to select the particular wavelength, while in case of the filter photometer, filter is used for this purpose. Thermo Scientific's Spectronic 20D+ is an example of single beam spectrophotometer. It has a range of 340 to 625 nanometers and a fixed effective bandwidth of 20 nanometers. The advantages of a single beam spectrophotometers are that they are easy to handle. Battery operated single beam spectrophotometers are easy to transport. The disadvantages are similar to that of a filter photometer. They are not practically useful for recording the spectra because manually adjusting the wavelength and recalibrating the spectrophotometer every time before use is very time consuming. The accuracy of a single beam spectrophotometer is limited by the stability of its source and the detector over time. Figure 5 represents the schematic representation of a single beam spectrophotometer. Double beam spectrophotometer. A double beam spectrophotometer minimizes the limitations of a single beam spectrophotometers in which the wavelength remains fixed. As the name suggests, this instrument involves two beams of radiations, one for the sample and the other for blank. The radiation's path is controlled by chopper, which alternates it between the sample, the blank and a shutter. The chopper's known speed of rotation is used by the signal processor to resolve the signal reaching the detector into the transmission of the blank PO and of the sample PT. It is possible to continuously adjust it to 0% transmittance by including an opaque surface as a shutter. In double beam spectrophotometer, the effective bandwidth is controlled by adjusting the entrance and exit slits of monochromator. The effective bandwidth values are usually around 0.2 to 3.0 nanometer. The automated recording of the spectra is carried out by the scanning monochromator. Double beam instruments are more versatile than the single beam instruments. They are useful for both quantitative and the qualitative analysis, but also are more expensive. Figure 6 represents the schematic representation of a double beam spectrophotometer. Diode array spectrometer. Photodiode array spectrometer consists of many photodiodes as detectors. The resulting array of detectors record an entire spectrum simultaneously in as little as 0.1 second. In a diode array spectrometer, the source radiation passes through the sample and is dispersed by a grating. The photodiode array is situated at the grating focal plane, with each diode recording the radiant power over the narrow range of wavelengths. Our diode array spectrometer is small and compact as it contains just grating in place of full monochromator. The signals are then processed by signal processor and the spectra are obtained. Figure 7 represents the schematic representation of a diode array spectrometer. The spectroscopy is a branch of science that involves the study of interaction of electromagnetic radiations with matter. Absorption takes place when energy from the radiative source is absorbed by the material. The UV visible spectroscopy works on the absorption phenomena and the principle is governed by Beer-Lambert's law. With all these informations here, we come to an end of today's lecture. Do keep in mind what we discussed today. I will be back with one more lecture in this series. If you want to learn more and enhance your knowledge, you may log on to our website www.cec.nic.in for MCQ, quizzes, LORs, etc. Thank you for your time today. I will see you in the next lecture. Have a great day.